Time is the silent force that structures our lives, every ticking second, every fleeting minute, the steady march of days into years. But what if I told you that time, the very thing we set our clocks by, isn't as absolute as it seems? Out there in the cosmos, time bends, warps, and even stands still in ways that defy everything we experience here on Earth. Picture this: a clock on a satellite orbiting our planet runs ever so slightly faster than one on the ground. Or imagine standing at the edge of a black hole, where time slows to a crawl for you while the rest of the universe speeds by in a blur. These aren't scenes from science fiction, they're real, measurable phenomena that challenge our most basic assumptions about reality. From the moment we wake up to the moment we sleep, time feels like a constant, unshakable rhythm. But the universe operates by a different set of rules, rules so strange that even the greatest minds in history have been left awestruck. Einstein's theory of relativity shattered the idea of universal time, revealing that it's not a rigid backdrop but a flexible, ever-changing fabric shaped by gravity and motion. And that's just the beginning. Across the cosmos, time behaves in ways that seem impossible, where a single second for one observer can stretch into millennia for another, where the past, present, and future blur into something far more mysterious. Today, we're diving deep into 30 mind-bending facts about time in the universe, revelations that will twist your perception of reality and leave you questioning everything you thought you knew. We'll explore how time speeds up and slows down in the presence of colossal cosmic forces, how black holes can freeze it entirely, and even how the very birth of the universe might hold clues to time's ultimate secrets. This isn't just a journey through space, it's an exploration of the most fundamental yet enigmatic dimension of existence. So buckle up, because by the time we're done, you'll never look at a clock the same way again. The universe is stranger than we can imagine, and time is its greatest illusion. Ever wondered what it would be like to stand at the edge of a black hole, the most extreme gravitational monster in the cosmos? According to Einstein's theory of relativity, time itself would slow to a crawl for you, while the rest of the universe speeds forward like a fast-forwarded movie. This isn't just theoretical, it's a real phenomenon called gravitational time dilation, and black holes are the ultimate proving ground. The sheer mass of these cosmic behemoths warps space-time so drastically that time runs slower near them compared to regions with weaker gravity. Picture a clock placed close to a black hole. If you could somehow see it from a safe distance, its hands would barely move, ticking sluggishly while your own watch races ahead. This eerie effect was famously brought to life in the movie Interstellar, where astronauts orbiting the black hole Gargantua experience hours while decades pass for those back on Earth. The science behind it is rock solid. Einstein's equations show that gravity doesn't just pull on objects, it stretches time itself. Near a black hole's event horizon, the point of no return, time slows so dramatically that it would almost appear to freeze from an outsider's perspective. You'd age mere seconds while the universe outside moves on without you. But here's the real twist: this isn't just some far-fetched quirk of physics. It happens on a smaller scale right here in our own cosmic neighborhood. Even Earth's gravity affects time, though the difference is minuscule. GPS satellites have to account for this, adjusting their clocks because time ticks slightly faster for them in orbit than it does down here on the surface. Black holes just take this effect to the extreme, bending time until reality itself seems to unravel. So the next time you glance at your watch, remember, time isn't as rigid as it seems. Out there in the depths of space, it's a fluid, ever-changing river shaped by the invisible hand of gravity. If you could hitch a ride on a beam of light, time would simply stop for you. That's not science fiction, it's one of the most astonishing consequences of Einstein's theory of relativity. At the speed of light, time dilation reaches its ultimate extreme. The faster you go, the more time slows down relative to someone standing still. But once you hit light speed, time doesn't just slow, It grinds to a complete halt. From the perspective of a photon racing across the universe, its entire journey, whether a few nanoseconds or billions of years, happens in an instant. This mind-bending reality comes with a staggering implication. If you could somehow travel at light speed, the entire universe would flash by in a blink. Distant galaxies, aging stars, the births and deaths of civilizations, all of it would happen simultaneously from your point of view. But there's a catch. Nothing with mass can ever reach this speed. The closer an object gets to light speed, the more energy it requires to keep accelerating. In fact, to push even a single atom to light speed would demand infinite energy, an impossibility bound by the laws of physics. Think of it like a cosmic speed limit. Just as you can't divide a number by zero, matter can't break the light speed barrier. Even hypothetical warp drives or wormholes, often floated in sci-fi as workarounds, don't actually let objects move faster than light. They bend space-time itself to cheat the system. This limitation isn't just a technicality, it's woven into the fabric of reality, ensuring cause and effect stay in order. If something could outpace light, it would effectively travel backward in time, violating causality and turning the universe into chaos. So while light speed time freeze is a thrilling thought experiment, it's also a reminder of the universe's unbreakable rules. Time may stretch and warp, but its flow can't be stopped for anything with mass. The speed of light isn't just a number, it's the guardian of cosmic order, keeping time's arrow pointing firmly forward. The twin paradox sounds like something straight out of a sci-fi novel, but it's one of the most fascinating demonstrations of how time isn't fixed, it's deeply personal. Imagine two identical twins. One stays on Earth living a normal life, while the other boards a spacecraft and blasts off at nearly the speed of light. When the traveling twin returns decades later, they step off the ship looking barely older, while their Earth-bound sibling has aged far more. This isn't just a wild hypothetical, it's a direct consequence of Einstein's special relativity, where motion warps the passage of time itself. At speeds approaching light, time dilation kicks in hard. The faster you move through space, the slower you move through time relative to someone at rest. For the twin on the spaceship, clocks, including their own biological clock, tick slower compared to those back home. From their perspective, the trip might feel like a few years, but Earth could have experienced centuries. The paradox isn't in the physics, but in our intuition. It feels contradictory because we're used to time behaving uniformly, yet the math doesn't lie. Real-world experiments have confirmed this effect, just on a smaller scale. In the 1970s, scientists loaded atomic clocks, some of the most precise timekeepers ever built, onto commercial jets flying at high speeds. After comparing them with clocks that stayed on the ground, they found the traveling clocks had indeed ticked slightly slower. The difference was tiny nanoseconds over hours, but it proved the principle. Even the slight speed of a passenger jet was enough to bend time, just as relativity predicted. What really twists your brain is realizing there's no correct time. Both twins' experiences are equally valid from their own perspectives. The traveling twin isn't somehow wrong. They genuinely experienced less time. This flips our everyday notion of a universal clock on its head. Time isn't a backdrop to the universe. It's a flexible, dynamic player in the cosmic dance. So the next time you complain about time flying by, remember, it literally does, depending on how fast you're moving. Time doesn't tick the same way everywhere, not even in our own solar system. Take Mercury and Jupiter, two planets where gravity bends time in wildly different ways. On Mercury, a small, fast-moving world with weak gravity, clocks run ever so slightly faster than here on Earth. But over on Jupiter, the solar system's heavyweight champion, time drags its feet. The planet's immense gravitational pull slows time down compared to lighter planets, meaning a clock on its surface would tick slower than one floating in space nearby. This isn't just theoretical. Space agencies like NASA have to account for these differences when planning missions. Each planet's gravity creates its own unique time zone, a concept known as gravitational time dilation. For example, when the Juno spacecraft orbited Jupiter, its onboard systems had to compensate for the fact that time passed differently there than at mission control back on Earth. Without these corrections, tiny timing errors could throw off navigation, communication, and even scientific measurements over long missions, the craziest part. These discrepancies add up. If you lived on Jupiter for a decade, you'd technically age slower than someone on Mercury, though the difference would only amount to a few seconds. But in the grand scheme of the cosmos, where gravitational extremes exist, these small variances become enormous. Imagine standing on the surface of a neutron star, where gravity is billions of times stronger than Earth's time that crawls at a snail's pace compared to the rest of the universe. Even our own moon has its own subtle time zone. Because it's smaller and less massive than Earth, clocks on the lunar surface tick just a fraction faster. Future lunar bases will need to sync their systems with Earth time, or else slight mismatches could complicate everything from day to transmission to synchronized experiments. Time isn't just a universal constant, it's a local phenomenon, shaped by the gravitational fingerprint of every world, star, and galaxy in existence. So the next time you glance at a clock, remember, it's only keeping time for this spot in space. Somewhere else, it's running at a completely different pace. The number 13.8 billion years gets thrown around a lot when talking about the age of the universe, but here's the twist. That figure isn't as straightforward as it seems. When we say the universe is 13.8 billion years old, we're talking about the time that's passed since the Big Bang from our perspective here on Earth. But due to the relentless expansion of space itself, the farthest galaxies we observe aren't just sitting at a fixed distance, they're racing away from us, carried by the stretching fabric of the cosmos. The light we see from them today began its journey billions of years ago when the universe was far smaller and denser. Here's where things get mind-bending. The most distant galaxy we've spotted, GNZ 11, is so far away that its light has traveled for roughly 13.4 billion years to reach us. But here's the kicker, because space has been expanding non-stop since that light was emitted. GNZ 11 isn't 13.4 billion light-years away anymore. In reality, it's now a staggering 32 billion light-years distant. That means we're seeing a snapshot of its infant phase, frozen in time, while the actual galaxy has long since moved far beyond that point. This creates a bizarre cosmic illusion. The observable universe is like a hall of mirrors where the past and present are tangled together. The deeper we look, the further back in time we peer, but the objects we're observing have since evolved, moved, or even vanished. Some of the earliest stars whose light washes over us today may have already burned out, their light just now arriving as a postcard from a bygone era. And there's another layer to this enigma. If the universe keeps expanding at an accelerating rate, as current evidence suggests, distant galaxies will eventually slip beyond our cosmic horizon, their light never reaching us again. Billions of years from now, future civilizations might peer into the sky and see only darkness where we once witnessed a sea of galaxies. The universe's age isn't just a number, it's a moving target shaped by the invisible push of dark energy and the endless stretch of spacetime. So when we say the universe is 13.8 billion years old, we're really just scratching the surface of a far stranger, more dynamic story. What if time, the very foundation of our daily existence, isn't fundamental at all? Down in the bizarre realm of quantum mechanics, where particles pop in and out of existence and reality flickers like a candle in the wind, time might not be the steady river we perceive, it could be an illusion. Theories like loop quantum gravity suggest time isn't woven into the fabric of the cosmos, but emerges from something deeper, like temperature arising from the motion of molecules. In this view, the universe at its smallest scales operates in a timeless state with no past, present, or future, just relationships between quantum events. Imagine a cosmic game of dominoes where each falling piece represents a quantum interaction. From our macroscopic perspective, we see a smooth sequence, a clear before and after. But zoom in close enough and the dominoes aren't falling in time at all. They're just arranged in patterns that appear to create a flow when we step back. That's the radical idea behind timeless physics. What we call time might just be a side effect of how quantum systems interact, a shadow cast by deeper mathematical structures. Loop quantum gravity takes this further by proposing that spacetime itself is granular, made of tiny, indivisible atoms of space and time. At these scales, the smooth continuity of time shatters into discrete steps like flipping through a cosmic flipbook. The kicker, beneath this granularity, there's no background clock ticking away, just relationships between quantum events defining what we perceive as sequence and duration. Even more startling, some interpretations of quantum mechanics suggest that without observation, reality exists in a fuzzy superposition where time loses all meaning until measured. This isn't just philosophical musing, it has real consequences for understanding black holes and the Big Bang. Near these extremes where gravity and quantum effects collide, our classical notion of time breaks down entirely. If time emerges rather than exists fundamentally, it could rewrite our understanding of the universe's birth. Was there a before the Big Bang, or does that question lose meaning in a timeless quantum foam? The answers might lie in a reality far stranger than clocks and calendars, one where time itself is just a mirage on the surface of something infinitely deeper. Ever watched a glass tumble off a table and shatter into pieces? That moment captures one of the universe's deepest secrets: why time only moves forward. The reason lies in a concept called entropy, the driving force behind the second law of thermodynamics. Simply put, entropy measures disorder, and this law states that in any closed system, disorder always increases over time. A glass breaking is the perfect example. It transitions from an ordered, intact state to a chaotic scattering of shards, and you'd never see those pieces spontaneously reassemble themselves. That irreversible slide toward disorder is what gives time its arrow, its one-way direction. But here's where it gets fascinating. Entropy doesn't just explain why broken glasses don't fix themselves, it underpins everything about how we experience time. Our memories, for instance, only work because entropy creates a record of the past. When you recall an event, your brain relies on physical changes, neurons firing in specific patterns, molecules shifting states, all of which leave traces that grow more disordered over time. That's why you remember yesterday but not tomorrow. The future remains an open book because entropy hasn't etched its mark yet. Zoom out to the cosmic scale, and entropy's role becomes even more profound. The early universe after the Big Bang was a hot, dense soup of particles in near-perfect order, a state of astonishingly low entropy. As the cosmos expanded and cooled, entropy began its relentless climb, driving the formation of galaxies, stars, and planets. Eventually, when the universe reaches maximum entropy, a hypothetical heat death, all energy will be evenly distributed, and time as we know it may lose all meaning. No more stars burning, no more processes creating order, just an eternal, unchanging equilibrium. This irreversible march toward disorder is why time feels so absolute in our daily lives. Eggs scramble but never unscramble, ice melts but never spontaneously refreezes. The universe is constantly sliding from rare, ordered states toward more probable, disordered ones. But there's a beautiful paradox here. Entropy's chaos is also what makes life possible. The increasing disorder releases energy, powers chemical reactions, and fuels the complexity that allows beings like us to exist. Time's arrow might point toward eventual cosmic stillness, but along the way it creates the very conditions for galaxies, planets, and minds to emerge. So next time you see a broken glass, remember, you're witnessing a fundamental law of reality in action, the silent force that shapes time itself. Time travel isn't just the stuff of science fiction under the right conditions. It's theoretically possible, at least when it comes to jumping into the future. Einstein's theory of relativity gives us a roadmap. Move fast enough or get close enough to an extreme gravitational force like a black hole, and time will slow down for you relative to everyone else. Imagine boarding a spaceship that accelerates to near light speed. For you, the trip might feel like a few years, but back on Earth, decades or even centuries could pass. Step off the ship and you'd find yourself in a world that's moved on without you, a future generations ahead of the one you left behind. Stephen Hawking was so fascinated by this idea that he once threw a party for time travelers with a twist. He sent out invitations after the event had already happened. The logic was simple. If time travelers from the future existed, they could have seen the invitation and popped back to attend. Hawking sat alone in a room with champagne and snacks, waiting. No one showed up. While it might seem like a playful experiment, it underscored a profound point. If time travel to the past were possible, we'd likely have evidence by now. But traveling to the future, that's a different story. Physics doesn't just allow it, it demands it under extreme conditions. The key lies in velocity and gravity. The faster you go, the more time dilates. At 99.9% the speed of light, a 5-year trip for you could mean over a century on Earth. Alternatively, park yourself near a black hole's event horizon, where gravity warps time so drastically that a few hours for you could translate to years elsewhere in the universe. Astronauts on the International Space Station experience a tiny taste of this orbiting at over 17,000 miles per hour. They age slightly slower than people on the ground. The difference is minuscule, but it proves the principle. So why haven't we built a time machine yet? The problem isn't the science, it's the engineering. Reaching near light speed requires unimaginable energy, and surviving near a black hole is, well, suicidal. But the universe itself provides examples. Cosmic rays particles hurled across space at nearly light speed experience extreme time dilation. A muon created in Earth's upper atmosphere should decay before reaching the ground, yet we detect them because, from their perspective, time slows down enough to survive the trip. In a sense, these particles are time travelers, experiencing mere microseconds while Earth's clock ticks onward. Hawking's empty party might have ruled out visitors from the future, but the door to forward time travel remains wide open. The universe is already doing it, we just haven't caught up yet. So while hopping backward in time might be off the table, the future, that's a destination waiting to be reached. All you need is enough speed or a black hole with patience. What if the passage of time is nothing more than an illusion, a trick of perception? The block universe theory proposes exactly that, suggesting past, present, and future aren't separate at all but exist simultaneously, frozen in a vast 4-dimensional structure where time is just another dimension like height or depth. Picture a DVD. Every scene is already encoded on the disc, from opening credits to final shot. Your experience of watching it unfold moment by moment doesn't change the fact that the entire movie is already there, complete. In this view, the universe works the same way. Your birth, your life, even events yet to come aren't fleeting. They're permanent fixtures in spacetime's unchanging landscape. This idea flips our everyday intuition on its head. We feel time as a river carrying us from one moment to the next, but physics suggests it might be more like a glacier, static and eternal. Einstein himself hinted at this when he wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion." His equations treat time as a coordinate, no different from spatial dimensions, implying that now is just a matter of perspective. To a hypothetical observer outside the universe, every event, dinosaurs roaming, civilizations rising, stars yet to ignite, would appear equally real, like points on a map. Critics argue this removes free will. If the future's already out there, are our choices just illusions? But proponents counter that the block universe doesn't dictate how events unfold, only that they are all part of the structure. Think of it like a novel. The ending is written, but the characters still make decisions that shape the story. Similarly, quantum mechanics introduces randomness at microscopic scales, meaning the block universe might be more like a branching tree than a predetermined script. Evidence for this mind-bending concept comes from relativity's success. GPS satellites, which rely on precise timing, only work because engineers account for time's flexibility, proof that space-time behaves as a unified fabric. Even the way we observe distant galaxies supports the idea. When we look at light from billions of years ago, we're literally seeing the past as it exists now in our reference frame. The block universe isn't just philosophy, it's a framework that helps explain why time behaves so strangely under extreme conditions. If true, death and birth, beginnings and endings, might just be waypoints in a cosmos where everything that ever was or will be is already set in stone, or more accurately, woven into space-time itself. The universe isn't just expanding, it's stretching time itself. When we look at distant galaxies billions of light years away, we're not just seeing across space, we're peering into a reality where time moves differently because of the relentless pull of cosmic expansion. Imagine space-time as a rubber sheet constantly being stretched. As light travels across this expanding fabric, its waves get pulled longer, shifting toward the red end of the spectrum, a phenomenon we call redshift. But here's the twist: this stretching doesn't just affect light. It subtly elongates time for distant events compared to how we experience it here and now. Take a supernova exploding in a galaxy 10 billion light-years away. From our perspective on Earth, the event appears to unfold in slow motion. The fiery demise of that star, which might last weeks in its own local time frame, could seem drawn out over months or even years to us. Why? Because the expansion of the universe has stretched not just the distance the light travels, but the very seconds and minutes it carries with it. This effect, called cosmological time dilation, means the farther out we look, the more time itself seems to decelerate in our observations. This isn't just a quirk of distant starlight, it's baked into the equations of general relativity. Einstein's theory predicted that expanding space would warp time, and modern telescopes have confirmed it. When astronomers study the light curves of faraway supernova, they notice a predictable slowing, a telltale sign that time isn't passing at the same rate everywhere. Even the cosmic microwave background, the afterglow of the Big Bang, carries this imprint. Its photons have been stretched so dramatically over 13.8 billion years that their original high-energy radiation has cooled into faint microwaves, a direct result of spacetime's expansion diluting both their energy and their perception of time. But the real mind-bender is this: for those hypothetical observers in those distant galaxies, time would feel perfectly normal. Their clocks tick at the same pace they always have. The difference only arises when comparing their time frame to ours across the vast, expanding gulf between us. It's as if the universe is a loaf of raisin bread baking in an oven. As the dough expands, every raisin moves away from every other, and light or time traveling between them has to cover more ground than it started with. The expansion doesn't just create distance, it rewrites the rules of how time connects one part of the cosmos to another. This cosmic time warp has profound implications for how we understand the universe's history. When we observe the earliest galaxies, we're not just seeing them as they were billions of years ago. We're seeing them in a state where time itself flowed differently relative to our present moment. The deeper we look, the more space-time stretching distorts our cosmic clock, making the ancient universe appear to unfold in a dreamlike slow motion. And if dark energy continues accelerating expansion, future astronomers might watch distant events grind to a near standstill, their light stretched into near eternity. Time isn't just a measure of change, it's a flexible thread woven into the fabric of an expanding universe, one that bends and twists with the cosmos itself. The very first second of the universe's existence was a frenzy of creation so extreme that our current laws of physics struggle to describe it. Picture this, an unfathomable trillionth of a second after the Big Bang. The entire cosmos was smaller than a single atom, yet hotter and denser than the core of any star. In this white-hot fireball, time itself was born, but not as we know it. At these energies, the fundamental forces we consider separate today, gravity, electromagnetism, and the nuclear forces, were unified into a single superforce, and time behaved more like a seething quantum foam than a steady progression. Within the first fraction of that second, an event called cosmic inflation occurred, where the universe expanded exponentially, doubling in size at least 60 times faster than the blink of an eye. This wasn't just rapid growth, it was space-time itself stretching at a rate that defies intuition. If you could witness it, a region smaller than a proton would have ballooned to the size of a grapefruit almost instantly. During this burst, quantum fluctuations were magnified into the seeds of all future structure, clumps of matter that would one day become galaxies. But here's the twist: inflation happened so fast that time, as we measure it, loses meaning. There wasn't even a clear before or after, just a quantum blur where cause and effect blur together. By the time the first full second arrived, the universe had cooled enough for quarks, the building blocks of protons and neutrons, to form from pure energy. Up until this moment, particles and antiparticles had been constantly annihilating each other, but a slight asymmetry in their numbers left behind just enough matter to eventually form everything we see today. Meanwhile, neutrinos, ghostly particles that barely interact with matter, flooded the cosmos in such numbers that their combined energy briefly dominated the universe. These particles still zip through you right now, billions per second, as silent relics of that first second. Yet the most mind-bending realization: our concept of time dissolves entirely at these extremes. The clock we rely on today, seconds, minutes, hours, had no reference in that primordial inferno. Without stable matter, without even fully formed space, time lacked the structure we associate with its flow. Some theories suggest time itself may have crystallized from this quantum chaos, emerging only as the universe cooled enough for orderly processes to take hold. That means the first second wasn't just the birth of the cosmos, it might have been the moment time as we know it truly began ticking. So when we talk about the universe's first second, we're not just describing an event in time, we're peering into the moment when time itself was forged. The closer we look, the more our familiar notions unravel, revealing a reality where beginnings and endings may be illusions painted onto a far stranger canvas. The Big Bang's opening act wasn't just the start of space, it was the origin of time's arrow, a fleeting instant where physics as we know it flickered into existence. Time crystals sound like something straight out of a futuristic fantasy, but they're very real, and they're rewriting the rules of physics as we know them. Unlike ordinary crystals, which have atoms arranged in repeating patterns in space, think of the symmetrical lattice of a diamond. Time crystals exhibit structure in time. Their atoms don't just sit in a fixed arrangement, they oscillate in a perpetual cycle, returning to their original state at regular intervals without any energy input. It's as if you had a clock that kept ticking forever without ever needing to be wound. This bizarre behavior defies one of physics' most fundamental principles, the idea that perpetual motion is impossible. Normally, any system left to itself will eventually settle into equilibrium, like a pendulum coming to rest. But time crystals break this rule by existing in a stable, non-equilibrium state, their atomic components flipping back and forth indefinitely, like dancers in a looped routine. The key to their motion isn't energy but quantum entanglement, the spooky connection between particles that Einstein famously called action at a distance. The discovery of time crystals sent shockwaves through the scientific community. First proposed by Nobel laureate Frank Wilczek in 2012, they were initially met with skepticism. How could something oscillate forever without violating thermodynamics? Yet by 2017, two separate teams, one at Harvard, another at the University of Maryland, had created time crystals in the lab using chains of ytterbium atoms and diamond defects chilled to near absolute zero. These experiments confirmed that time crystals weren't just theoretical curiosities. They were a new phase of matter, as real as solids or liquids. What makes them so revolutionary isn't just their defiance of classical physics, it's their potential to turbocharge quantum computing. Traditional quantum bits or qubits are notoriously fragile, losing coherence at the slightest disturbance. But time crystals, with their built-in rhythm and resistance to external noise, could serve as ultra-stable qubits, maintaining quantum information far longer than current systems. Imagine a quantum computer where calculations aren't derailed by tiny temperature fluctuations or electromagnetic interference. Time crystals might be the missing ingredient to make large-scale quantum computing practical. Beyond technology, these strange structures hint at deeper mysteries. Could time crystals reveal new layers of symmetry in the universe? Might they help us understand how time itself emerges from quantum mechanics? Some theorists even speculate that certain cosmic phenomena, like pulsars or black hole horizons, could exhibit time crystal-like behavior on a stellar scale. One thing's certain, in a universe where matter can dance to the beat of its own eternal clock, our understanding of time and reality will never be the same. When two black holes spiral toward each other in a cosmic dance, they don't just warp space, they send tremors through time itself. These ripples, known as gravitational waves, were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, confirming Einstein's century-old prediction. But what's often overlooked is how these waves don't merely distort space, they stretch and compress time as they pass through everything in their path, including you. Picture the aftermath of a black hole collision billions of light-years away. As the resulting gravitational waves race outward at light speed, they alternately squeeze and expand spacetime in their wake. If one of these waves passed through your living room, the distance between your couch and TV would briefly shrink, then stretch, and so would the flow of time. Your watch would speed up imperceptibly as the wave compressed spacetime, then slow down as it expanded. These fluctuations are vanishingly small, a fraction of a proton's width over Earth's entire diameter, but they're real. LIGO detectors work by measuring these minuscule distortions in spacetime, using lasers to track how the passage of a gravitational wave changes the length of its 4-kilometer arms. The craziest part, these waves carry fingerprints of the events that created them. When LIGO detected its first signal, the waveform revealed details about the black hole's masses, spins, and even their final milliseconds before merging. As the holes circled each other hundreds of times per second, their gravitational waves became a siren song of warped time, encoding information about the most violent events in the universe. Future observatories like the space-based LISA mission will listen for even lower frequency waves, potentially uncovering mergers from the universe's first billion years. Gravitational waves aren't just cosmic messengers, they're proof that time is as malleable as clay. Every massive object that accelerates creates them, from neutron stars to supernova, each leaving its own imprint on the fabric of spacetime. Even you generate gravitational waves when you move, though they're weaker than a whisper in a hurricane. The universe is alive with these ripples, a symphony of stretching and compressing time, reminding us that the clock we rely on is far more fluid than it seems. The farther out into space we look, the more time itself seems to slow down, not because distant galaxies are moving through space, but because space itself is stretching beneath them. This eerie effect, called cosmological time dilation, means a supernova explosion in a galaxy 10 billion light-years away unfolds in slow motion from our vantage point. The culprit, the Hubble flow, the relentless expansion of the universe that causes distant objects to recede from us faster than nearer ones. As their light travels across this expanding spacetime, its waves get stretched like taffy, shifting toward the red end of the spectrum. But redshift isn't just about color, it's a direct imprint of time being stretched too. Think of it like a cosmic game of telephone where the message isn't just traveling, it's being pulled apart en route. When photons from that distant supernova began their journey, the universe was nearly 30% smaller than it is today. By the time the light reaches us, space has expanded so much that the intervals between the photons' wave crests have widened. Since light's frequency acts like a clock, with each oscillation marking a tick, this stretching makes events in faraway galaxies appear to unfold slower than they actually did locally. A star that took 2 weeks to explode might seem to dim over months from our perspective, its final moments dragged out by the universe's expansion. This isn't some optical illusion, it's been measured. Astronomers studying Type 1a supernova, stellar explosions with predictable brightness curves, noticed their light faded slower the farther away they were. The pattern matched Einstein's equations perfectly. For every doubling of distance, the supernova's clock ran half as fast relative to ours. Even the cosmic microwave background, the afterglow of the Big Bang, carries this temporal fingerprint. Its photons, emitted when the universe was just 380,000 years old, have been redshifted so dramatically that their original high-energy radiation now reaches us as faint microwaves, a cold echo of a hotter, denser past. But here's the twist: observers in those distant galaxies wouldn't feel time passing any differently. Their local clocks, whether atomic vibrations or biological aging, tick normally. The dilation only emerges when comparing their time frame to ours across the vast, expanding gulf between us. It's like two musicians playing the same song on opposite ends of a speeding train. Both hear the correct tempo locally, but to the listener outside, the music from the far end sounds deeper and slower as the train's motion stretches the sound waves. This cosmic time warp has startling implications. If we could watch a planet orbiting a star at the edge of the observable universe, its years would crawl by from our perspective, each revolution taking millennia to complete. Yet for life forms on that world, time would feel utterly normal. The Hubble flow doesn't just separate galaxies in space, it fractures the very synchronization of time across the cosmos. As the universe's expansion accelerates, driven by dark energy, this effect will only grow more extreme. Billions of years from now, light from distant galaxies may redshift so severely that their clocks will appear frozen altogether, their signals stretched into near-infinite slowness before fading from view entirely. The Hubble flow reveals time as a local phenomenon, its rhythm dictated by the stretching fabric of spacetime. Far from being a universal metronome, time is a flexible, elastic thing, its beat changing with the vastness of cosmic distances. Each photon reaching us from the depths of space isn't just a messenger from the past, it's a testament to time's fluidity, a reminder that the universe's expansion doesn't just move galaxies apart. It rewrites time's very tempo across the void. What if our universe isn't the first or the last to exist? The Big Bang marks the beginning of our cosmic story, but some theories propose time didn't start there. Imagine a cosmic cycle where universes are born, expand, and collapse, only to rebound anew in an endless loop. This idea, known as the cyclic model, suggests our Big Bang wasn't a true beginning, just the latest chapter in an infinite series. In this view, time stretches backward without end, each universe inheriting traces of its predecessor. The equations even allow for a kind of cosmic memory, where black holes from one cycle might seed structure in the next. Then there's the multiverse hypothesis, where our universe is just one bubble in a vast froth of realities, each with its own laws of physics and arrow of time. Some of these sibling universes could have existed long before ours, their timelines running parallel or intersecting in ways we can't yet fathom. String theory takes this further, proposing higher dimensional membranes or brains colliding to spark big bangs like ours. In these scenarios, time might flow differently in other universes or even backward, with entropy decreasing instead of increasing. But how do we grapple with the idea of before, when time as we know it began at the Big Bang? Some physicists argue the question is meaningless, like asking what's north of the North Pole. Others suggest time might emerge from something deeper, like quantum entanglement or mathematical structures beyond spacetime. The most radical theories propose a timeless multiverse where causation loops back on itself, making before and after irrelevant. While these ideas remain untestable for now, they push the boundaries of imagination. If time existed before our universe, it rewrites not just cosmology but philosophy. Are we one link in an infinite chain? Is time's arrow universal or just a quirk of our local reality? Until we crack quantum gravity or glimpse beyond our cosmic horizon, these questions linger, haunting reminders that the universe's greatest mysteries might lie not in the stars but in the very fabric of time itself. Down at the smallest scales imaginable, time itself might break apart into tiny, indivisible fragments like a movie reel made of individual frames too quick for even the universe to perceive. This mind-bending possibility comes from the concept of Planck time, the shortest meaningful interval that physics allows, 10 to the power of negative 43 seconds. To put that into perspective, if you divided a single second into as many pieces as there are atoms in the observable universe, you still wouldn't come close to how infinitesimally small a Planck time is. At this scale, the smooth, flowing time we experience in our daily lives could give way to something far stranger, a pixelated spacetime where change happens not as a continuous glide, but in discrete quantum jumps. The idea stems from the marriage of quantum mechanics and general relativity. In the quantum realm, energy isn't smooth, it comes in packets called quanta. Light, for example, is made of photons, tiny bundles of energy that can't be divided further. If energy is granular, why not spacetime itself? Theorists like Carlo Rovelli, a pioneer in loop quantum gravity, suggest that just as a digital image reveals pixels when you zoom in far enough, spacetime might resolve into fundamental atoms of time and space at the Planck scale. In this view, time doesn't flow like a river, it ticks like a cosmic clock with the smallest possible increments, each Planck time marking a quantum of change in the universe. Imagine flipping through a flipbook where each page represents a Planck moment. Normally, flipping fast enough makes the images appear seamless, just like how our macroscopic reality feels continuous. But if you could slow the flipbook to Planck time intervals, you'd see the individual frames, revealing gaps between moments where time's progression is more like a series of snapshots than a smooth film. Some models even propose that between these Planck-sized ticks, there's no meaningful notion of before or after, just a frothy quantum uncertainty where causality itself blurs. This granularity could solve one of physics' biggest headaches, the singularity at the heart of black holes and the Big Bang. In classical physics, these points have infinite density where space-time curvature becomes nonsensical. But if time and space are pixelated at the Planck scale, there's a built-in limit, a smallest possible volume and shortest possible time where the equations stop breaking down. No infinities, no singularities, just the universe's fundamental resolution stepping in like a safety net. Yet here's the catch, we can't directly observe this quantum foam of spacetime. The Planck scale is so unimaginably tiny that probing it would require particle accelerators the size of galaxies, or energies so extreme they'd collapse into black holes. For now, Planck time remains a mathematical beacon, guiding theories like loop quantum gravity and string theory toward a deeper understanding of reality's fabric. But if it's real, it means time isn't just relative, it's digital at its core, ticking away in the universe's smallest, most secret beats. And just as pixels shape an image without us noticing them individually, these quantum ticks might quietly structure every moment we perceive as the unbroken flow of time. Wormholes aren't just cosmic shortcuts, they could be gateways to the past or future. Imagine folding a piece of paper so two distant dots touch, then poking a pencil through to connect them. That's the basic idea behind wormholes, theoretical tunnels through space-time that could link not just different locations but different moments in time. Einstein's equations allow for their existence, but here's the catch. They'd require exotic matter with negative energy to stay open, something we've never observed naturally. Picture stepping into one end of a wormhole while the other end accelerates to near light speed. Due to time dilation, minutes could pass for the moving end while centuries fly by outside. Exit the wormhole and you'd emerge in a different era. Theoretically, you could even create a loop where the wormhole's own gravitational fields twist time into a circle, allowing travel to moments before you entered. But don't pack your bags for the Jurassic period just yet. Wormholes are notoriously unstable without exotic matter. They'd collapse faster than an inflatable pool with a hole. And even if they existed, the energy required to stabilize one would dwarf anything humanity could produce. Still, their mathematical possibility keeps physicists intrigued. As theoretical time machines, wormholes remind us that the universe's rulebook might be far stranger than we've dared to dream. Think about rewinding the cosmic clock to just a few 100 million years after the Big Bang. Back then, the universe was a crowded, chaotic place packed with hot, dense gas and blazing infant stars. Here's the wild part. In that primordial soup, time itself moved slower than it does today. Not because some cosmic force was hitting the brakes, but because gravity's relentless pull literally warped the flow of time. The early universe's extreme density meant space was so tightly curved that clocks, if any existed back then, would have ticked at a fraction of their current speed when compared to the vast, diluted cosmos we inhabit now. Evidence for this comes from quasars, the brilliant beacons powered by supermassive black holes in the young universe. Astronomers studying these objects noticed something peculiar. Their light variations, like flickers in brightness that should happen over days or weeks, appear stretched out when we observe them across billions of light years. A fluctuation that might last 10 days in a nearby quasar could appear to unfold over 15 days in one from the early universe. This isn't just an optical illusion or a trick of distance. It's a direct imprint of time dilation caused by the universe's denser, more warped past. The math behind this is rooted in Einstein's general relativity. Just as a clock ticks slower near a black hole due to intense gravity, the whole early universe functioned like a high-gravity environment because matter and energy were crammed so tightly together. As the cosmos expanded, that density dropped and spacetime's curvature relaxed, allowing time to speed up in a cosmic sense. Imagine a rubber band stretched taut, vibrations travel slower through its tense fibers. But loosen it and waves move faster. Similarly, the universe's expansion has loosened spacetime's grip on time itself, letting the cosmic clock tick ever faster as emptiness grows. There's a stunning consequence to this. If you could teleport back to the universe's first billion years, your wristwatch would gradually fall out of sync with the rest of reality. A minute for you might pass while an hour and a half elapsed in today's far-flung, low-density cosmos. Even the afterglow of the Big Bang, the cosmic microwave background, holds clues. Its fluctuations, frozen in time, show patterns that would have oscillated slower in the early universe's thicker medium, like sound waves traveling through molasses instead of air. But here's what really bends the mind. This doesn't mean the early universe felt sluggish to anyone living there. Local physics always appears normal to local observers. A second still felt like a second to particles in that ancient fireball. the dilation only emerges when comparing their time frame to ours across the chasm of cosmic history. It's like two metronomes ticking at different speeds in separate rooms. Each keeps perfect time in its own space, but side by side, their mismatch becomes obvious. As dark energy accelerates the universe's expansion, this effect will only grow more pronounced. Billions of years from now, any hypothetical observers might look back at our era and see time dragging in our dense, crowded galactic neighborhoods compared to their even more thinly stretched void. The cosmic clock never stops changing, and with every passing moment, the universe quietly rewrites the rules of time itself. In the quantum realm, particles play by rules that make time seem like an afterthought. Take Schrödinger's famous cat the thought experiment, where a feline in a box is simultaneously alive and dead until someone peeks inside. While this paradox highlights the weirdness of quantum superposition, it also reveals something startling about time itself. A particle in superposition doesn't just exist in multiple states, it effectively exists in multiple timelines at once, as if the past, present, and future are all happening concurrently until the moment of observation forces a single outcome. This isn't just theoretical sleight of hand. Experiments with photons and electrons show that unobserved particles really do occupy all possible states simultaneously, like a cosmic game of choose-your-own-adventure where every path is taken until the book snaps shut. In the famous double-slit experiment, a single particle passes through two openings at the same time, interfering with itself as if it's traversing parallel realities. Only when scientists try to measure which slit it went through does the particle pick a definitive path. Until then, it's as if time branches into countless possibilities, with the particle experiencing them all at once. The implications for time are mind-bending. If a quantum system can straddle multiple states, and by extension, multiple potential futures until observation collapses it into one, then the line between before and after blurs into a fog of probabilities. Some interpretations of quantum mechanics, like the many worlds hypothesis, take this further, suggesting that every possible outcome does happen, splitting the universe into infinite branches where each version of events plays out. In this view, time isn't a straight line but a sprawling tree, with every quantum decision spawning new realities where different moments unfold. Even stranger, quantum entanglement, where particles remain mysteriously linked across vast distances, hints that time might not flow uniformly at microscopic scales. Experiments show that measuring one entangled particle instantly determines its partner's state, even if they're light years apart. This spooky action at a distance seems to defy causality, as if the particles communicate faster than light or exist outside time's usual rules. Some theorists suggest entanglement could be a kind of time loop, where cause and effect circle back on themselves in ways our classical intuition can't grasp. The real kicker, this quantum timelessness might not be confined to tiny particles. If superposition scales up, as some experiments with large molecules suggest, then macroscopic objects, or even entire systems, could theoretically exist in blurred states of time until observed. Imagine a cosmic version of Schrödinger's cat where entire stars or galaxies hover in unresolved states, their histories and futures undecided until some universal observer locks them into place. It's a dizzying thought. Time as we know it might be an emergent property, a side effect of countless quantum observations stitching reality together moment by moment. So the next time you check your watch, consider this: the steady tick of seconds might just be an illusion, a smoothed-over approximation of a far weirder truth. Down at the quantum level, time isn't a river flowing in one direction. It's more like a stormy sea, with waves of possibility crashing in all directions at once until the act of looking forces the chaos into something we recognize as now. We like to think of time as something fixed and universal, a steady drumbeat measured by clocks and calendars, but here's the uncomfortable truth. the way we slice time into hours, minutes, and time zones is entirely human-made. Ancient civilizations tracked time using the sun's arc or the moon's phases, but these natural rhythms are messy. A day isn't always exactly 24 hours. Earth's rotation slows infinitesimally over millennia due to tidal friction. Even our neat 12-month calendar is a compromise, cobbled together from Roman politics and astronomical approximations, leaving us with months that range from 28 to 31 days for no reason other than historical tinkering. Newton envisioned time as an absolute river flowing uniformly across the universe, independent of anything else, but Einstein shattered that illusion. His relativity revealed that time bends like taffy around massive objects and stretches or shrinks depending on how fast you're moving. A GPS satellite orbiting Earth experiences time slightly faster than your phone on the ground, a difference engineers must correct to keep navigation accurate. This isn't some abstract quirk, it's proof that time isn't a backdrop to reality but an active participant, shaped by gravity and motion. Consider time zones, another human invention born out of railroad schedules, not nature. Before the 19th century, towns set clocks by local noon when the sun peaked overhead. But trains crossing vast distances needed standardization, so we carved the world into artificial slices. Even now, political decisions warp time. China, which could span 5 time zones, uses just one nationwide, while Nepal sits at a quirky 15 minutes ahead of India simply because it refused to sync with its neighbor. Yet nature refuses to conform. The moon's cycle doesn't match our months, and Earth's wobbly orbit ensures no 2 years are perfectly identical. Plants and animals follow circadian rhythms tuned to daylight, not atomic clocks. Some desert beetles use the Milky Way's glow to navigate at night, a celestial clock utterly indifferent to human timekeeping. Meanwhile, deep in the cosmos, pulsars spin with near-perfect regularity. Their rhythmic flash is a cosmic metronome untouched by human constructs. The takeaway: time as we measure it is a practical fiction, one that keeps trains running and meetings scheduled but bears little resemblance to the universe's fluid, chaotic reality. Newton's absolute clockwork universe was elegant, but Einstein's flexible spacetime is the one we actually live in. So the next time you complain about daylight saving time or a leap second, remember, the universe never agreed to our rules in the first place. What does now really mean? Right this second, as you watch this video, you might feel certain that this moment, the present, is something solid and universal. But physics paints a far stranger picture. Einstein's relativity tells us there's no such thing as a single, objective now that everyone in the universe agrees on. What's happening at the same time? For you could already be the past for someone moving at high speed or future for someone near a black hole. The present isn't a fixed point, it's a fluid, personal experience woven into the fabric of spacetime itself. Think of 2 lightning strikes hitting opposite ends of a moving train. To someone standing on the platform, the strikes appear simultaneous. But for a passenger sitting in the middle of that speeding train, the strike at the front happens first because the train's motion means the light from the rear strike takes slightly longer to reach them. Neither observer is wrong, they're just experiencing different versions of now based on their movement. This revelation, called the relativity of simultaneity, shatters the illusion that the present moment is something everyone shares. There's no universal clock ticking in sync across the cosmos, just countless overlapping nows, each valid in its own reference frame. This gets even weirder when you consider cosmic distances. Suppose an alien civilization in the Andromeda Galaxy, 2.5 million light-years away, is hosting a grand celebration right now, as we define now on Earth. By the time their light reaches us, that party will have been over for millions of years. Conversely, if we could instantly ask them what they're observing now, Earth in their present would show dinosaurs roaming because that's the light just arriving there. The present isn't just relative, it's fractured across the vastness of space, with every point in the universe living in its own isolated slice of time. Even quantum mechanics complicates things. At microscopic scales, particles can exist in superpositions multiple states at once, until observation collapses them into a definite state. If reality at its most fundamental level doesn't choose a state until measured, does the present moment truly exist independently of observation? Some interpretations suggest the now we experience might be an emergent property, a consequence of countless quantum events resolving into something our brains perceive as a continuous flow. Philosophers have wrestled with this for centuries. Is the present just an infinitesimal sliver between past and future? Or is it all that truly exists, with past and future being mental constructs? Physics offers no easy answers. The equations of general relativity treat time as a dimension where all events exist eternally, like frames in a film strip, while quantum mechanics dances around the idea that reality might be assembling itself moment by moment. We're left with a paradox. The present feels viscerally real to us, yet the deeper we probe, the more it dissolves into the tangled knots of relativity and quantum uncertainty. So the next time you pause to savor a moment, remember, you're not just experiencing time, you're shaping it, defining your own personal now, in a universe where no two clocks ever truly agree. The present isn't a place we all inhabit together. It's a story each of us tells ourselves, a fleeting alignment of space-time that vanishes as soon as we try to pin it down. Every time you check your phone's GPS to navigate, you're relying on a hidden cosmic correction, one that accounts for time itself running slightly faster in space than on Earth. The satellites powering your maps orbit at about 8,700 miles per hour, fast enough for Einstein's special relativity to speed up their onboard clocks by roughly 7 microseconds per day. Meanwhile, Earth's gravity tugs time in the opposite direction. General relativity slows those same clocks down by about 45 microseconds daily compared to the surface. Add these effects together and satellite clocks gain a net 38 microseconds each day. That might sound negligible, but in the world of precise positioning, where light travels nearly a foot in a nanosecond, those tiny errors would throw off your location by over 6 miles within a single day if left uncorrected. Here's how it works in practice. Each GPS satellite carries an atomic clock synchronized with ground stations. As the satellite beams signals to your phone, those signals include timestamps marking when they were sent. Your device calculates how long the signals took to arrive, multiplying that duration by the speed of light to determine distance. But if the satellite's clock were running unchecked, its slight time gain would make those timestamps inaccurate. The signals would appear to have taken longer than they actually did, tricking your phone into thinking the satellite was farther away than reality. Multiply this error across multiple satellites, and suddenly your "turn left in 500 feet" prompt could place you in the wrong neighborhood. This isn't just hypothetical. Early GPS prototypes didn't account for relativity, and engineers quickly noticed discrepancies piling up. By the time the system went live in the 1980s, relativity corrections were baked into the software. Today, every GPS device from your smartphone to aircraft navigation systems depends on these adjustments. Even the slight gravitational difference between satellites in medium Earth orbit and ground stations matters. If a satellite's orbit dips closer to Earth, where gravity is stronger, its clock slows by an extra fraction of a microsecond. Engineers track these variations in real time, tweaking the signals to keep everything precise. The craziest part, this same principle governs timekeeping across the cosmos. Pulsars spinning neutron stars that flash like cosmic lighthouses experience extreme gravitational time dilation. Their surfaces are so dense that clocks there would tick at half the rate of Earth's. If aliens near a pulsar tried using GPS, they'd need far wilder corrections than we do. Even on Earth, time dilation isn't uniform. A clock on Mount Everest ticks marginally faster than one at sea level because gravity weakens with altitude. Over decades, the difference would amount to a few extra microseconds, not enough to notice in daily life, but enough to throw off particle colliders or global financial networks synced to atomic time. So the next time your phone guides you through an unfamiliar city, remember, you're not just using space-based tech, you're tapping into humanity's hard-won understanding of time's flexibility. Those satellites orbiting overhead are more than navigational aids. They're proof that Einstein's once controversial ideas now quietly steer our modern world, one corrected microsecond at a time. The Big Bang marks the origin of our universe, but it also presents a paradox that keeps philosophers and physicists awake at night. If time itself began at that moment, what could possibly have come before? The question feels natural to ask, yet the very framework of physics suggests it might be meaningless, like asking what's north of the North Pole. In the equations of general relativity, time isn't just a feature of the universe, it's part of the cosmic fabric that emerged with space and matter. Trying to imagine a before the Big Bang is like trying to picture what's outside the edge of a bubble. There's no outside to speak of because the bubble defines the boundaries of existence. Some theories push beyond this limitation. Quantum gravity models like loop quantum cosmology propose that the Big Bang wasn't a true beginning but a bounce from a previous universe that collapsed. Imagine the cosmos as an accordion, contracting to a point before springing outward again. Time in this view is cyclical, stretching infinitely backward and forward. String theory entertains even wilder possibilities, like colliding higher dimensional membranes sparking big bangs like cosmic fireworks in an eternally existing multiverse. These ideas dance at the edge of science, offering mathematical elegance but little empirical proof. Theologians and metaphysicians have wrestled with this puzzle for centuries. The concept of creatio ex nihilo, creation from nothing, appears in religious traditions worldwide, suggesting a reality beyond time's arrow. Augustine of Hippo, grappling with the nature of time in the 4th century, argued that time was part of God's creation with no before existing outside it. Modern physics echoes this in secular terms. If space-time and quantum fields arose together, asking what preceded them might be as nonsensical as asking what's louder than silence in a vacuum. Yet the human mind rebels at the idea of absolute beginnings. We instinctively search for causes, chains of events, a framework where every now follows a then. This cognitive itch drives theories like conformal cyclic cosmology, where universes endlessly repeat in a loop, or the holographic principle, where our three-dimensional reality is a projection of information encoded on a two-dimensional boundary. Some even speculate that the universe is a self-contained causal loop, where the Big Bang was triggered by its own future, a twist that dissolves linear time into a Möbius strip of cause and effect. The trouble is testability. Without evidence, these ideas drift into metaphysics, beautiful thought experiments with no clear path to verification. The Planck era, the first fraction of a second after the Big Bang, is shrouded in quantum uncertainty where known physics breaks down. Until we uncover a theory of quantum gravity or detect relics of a pre-Big Bang universe like phantom imprints in the cosmic microwave background, the question lingers in the realm of speculation. What's startling is how this edges science toward questions once reserved for philosophy or theology. If time had a beginning, did it need a beginner? Or is the universe its own cause, a self-contained loop of physics that demands no external explanation? The line between profound science and untestable metaphysics blurs here, revealing how deeply our understanding of time is intertwined with our hunger for origins. The Big Bang didn't just ignite the cosmos, it ignited a mystery that challenges the very foundations of how we think about existence. Einstein's equations contain a strange loophole that could turn time travel from fiction into physics, closed time-like curves or CTC. These are paths through space-time where the future loops back to meet the past, creating a cosmic Möbius strip where cause and effect twist into a circle. Picture a hiker walking in a straight line only to find themselves back at their starting point, except instead of space, it's time itself that bends into a loop. In a CTC, you could theoretically set off on a journey and return before you ever left, meeting your past self in a paradox-free cycle. The mathematics behind this is surprisingly solid. Certain solutions to general relativity, like the Gödel universe or a rotating cosmic string, allow for CTCs where time loops back on itself without violating known physics. Even wormholes, if stabilized by exotic matter, could be shaped into time machines where one end accelerates to create a temporal bridge, the key difference from Hollywood's chaotic time travel plots. CTCs enforce self-consistency. Any action taken in the loop must seamlessly fit into the timeline, like a snake swallowing its own tail. Try to change the past, and the universe would conspire to prevent contradictions. A dropped glass might slip from your fingers just before you can shatter it, preserving history as it always was. This idea isn't just theoretical playfulness. Physicists like Kip Thorne have shown how carefully arranged wormholes could create closed time-like curves under precise conditions. Imagine two wormhole mouths initially synchronized in time. If you drag one mouth near a black hole or accelerate it to near light speed, time dilation would cause it to age slower than its stationary twin. Step through the accelerated mouth, and you'd exit the other side in the past relative to your departure point. Connect these mouths in space, and voila, you've built a time loop where yesterday and tomorrow exist side by side. Nature seems to abhor these loops, though. The Novikov self-consistency principle suggests any attempt to create a paradox would be thwarted by quantum mechanics or hidden variables. Want to go back and prevent your own birth? Some fluke, a jammed gun, a sudden distraction would inevitably intervene. This isn't just speculation. Quantum experiments with particles entangled across time hint that the universe might prevent paradoxes at a fundamental level. Yet the biggest obstacle isn't logic, it's energy. Creating a CTC would require negative energy densities to hold a wormhole open or warp spacetime into a loop, something we've never observed naturally. Quantum field theory allows for microscopic amounts of negative energy, but scaling it up to human-sized time machines seems impossibly distant. Even if achievable, the cosmic censorship hypothesis suggests black holes might erase CTCs behind event horizons, hiding them from causality's reach. For now, closed time-like curves remain a tantalizing quirk of relativity's math, a reminder that time isn't just a line but a landscape with hidden folds and tunnels. They tease us with the possibility of loops where past and future touch, where history isn't set in stone but a dynamic tapestry still weaving itself. Until we find a way to probe these extremes, CTCs linger at the edge of science and dream, challenging us to rethink not just how time flows, but whether it flows at all or merely spirals in ways we're just beginning to glimpse. Imagine a universe so old and cold that even the last embers of stars have flickered out. Black holes, the final survivors of cosmic time, have evaporated into faint whispers of radiation. The once vibrant cosmos has settled into an eternal, uniform darkness where no heat flows, no structures form, and no change occurs. This isn't dystopian fiction. It's the inevitable fate our universe is hurtling toward, known as heat death. And in this frozen equilibrium, time itself may lose all meaning. Here's why. Time, as we understand it, depends on change, the movement of energy from hot to cold, the transformation of matter, the irreversible march of entropy. But in a heat-dead universe, entropy has reached its maximum. Like a cup of coffee left untouched until it matches room temperature, every corner of the cosmos settles into perfect thermal balance. With no temperature differences, no energy gradients, nothing can happen. No stars ignite, no particles collide, no clocks tick. The universe becomes a static tapestry where before and after are indistinguishable. Without processes to mark its passage, time ceases to function as anything but an abstract coordinate, an empty dimension with no events to fill it. This chilling scenario emerges from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in a closed system. Our universe started in a state of astonishingly low entropy, the hot, dense soup of the Big Bang. Over billions of years, that initial order unraveled as matter clumped into galaxies, stars forged heavy elements, and life emerged to burn energy. But every step of this grand history came at a cost. Each conversion of energy released waste heat, pushing the cosmos closer to maximum entropy. Eventually, even the most efficient engines, like the supermassive black holes slowly radiating away via Hawking radiation, will exhaust their fuel. The universe will reach a state of quantum silence where the very concept of now stretches into infinity. But what does this mean for time's arrow? In our everyday lives, time's direction is obvious. Eggs don't unscramble, memories accumulate, and we age. This asymmetry stems from entropy's rise, giving time its forward thrust. In a heat-dead cosmos without entropy gradients to drive change, the distinction between past and future evaporates. There's no flow because there's nothing to flow toward. Some physicists speculate that in this state, the equations of general relativity would allow time to become space-like, a dimension where you could move backward as easily as forward, if only there were any energy left to do so. Yet here's the haunting beauty of it all. Heat death isn't oblivion. The universe isn't disappearing, it's simply settling into its most probable, lowest energy state. All the energy that ever existed remains, but it's smeared so thinly across the void that it can't power even a single electron's jump between atomic levels. Quantum fluctuations might still spark rare, fleeting events over incomprehensible timescales. Think a lone atom vibrating once every trillion years. But for all practical purposes, the universe has run its course. Civilizations that might arise in the distant future would find no resources to harness, no thermodynamic gradients to exploit. Their history would be written in the fading warmth of a cosmos that long ago forgot how to change. So while heat death sounds like an ending, it's really a transformation, the universe trading its dynamic youth for an eternal, quiet maturity. Time, that relentless force we set our watches by, may ultimately be nothing more than a temporary phenomenon, a side effect of the cosmos's journey from order to disorder. And when that journey is complete, time as we know it could dissolve into the infinite silence of a universe that's done counting. Ever swatted at a fly only to watch it zip away effortlessly? That split-second escape isn't just quick reflexes, it's a glimpse into a world where time moves slower for them than for us. Flies experience life in something like slow motion, their rapid-fire metabolism and tiny nervous systems processing information at speeds that would leave us dizzy. To a housefly, your hand descending in what feels like a blink to you might seem like a leisurely drift through molasses. This phenomenon, known as temporal resolution, varies wildly across species, shaped by body size, metabolism, and even environmental need. Smaller creatures with faster heartbeats often perceive time at higher frame rates, while larger, slower-moving animals operate on a more languid timescale. Take hummingbirds whose wings beat up to 80 times per second. To them, the world unfolds in hyper-detailed increments, each millisecond crammed with sensory input we'd miss entirely. Contrast this with giant tortoises whose heart rates can drop to a few beats per minute. Their reality is a drawn-out tapestry where seconds blend into minutes, and a single bite of cactus might unfold like a slow-motion film reel. These differences aren't just quirks, they're survival tools. Predators like dragonflies, with eyes that detect movement at 300 frames per second, see the world as a series of frozen snapshots, letting them pinpoint prey mid-air. Meanwhile, deep-sea creatures lurking in near-lightless abysses might operate on a glacial timescale, conserving energy where every millisecond counts less than patience. Now stretch this concept beyond Earth. Imagine a planet with gravity 10 times stronger than ours, where the crushing weight of an entire world slows time itself. Alien life forms evolving there wouldn't just move sluggishly, they'd perceive existence in a distorted temporal crawl. To them, a single heartbeat might span what feels like hours to us, their biology adapted to a reality where chemical reactions, neural signals, and even atmospheric changes unfold at a fraction of Earth's pace. Conversely, on a tiny, low-gravity moon, creatures might live lives of frenetic speed, their metabolisms buzzing like hummingbirds on overdrive, experiencing a human lifetime's worth of events in what we'd measure as months. This isn't just speculative biology, it's grounded in physics. Einstein's relativity tells us gravity warps time, meaning high-gravity worlds would literally bend the flow of seconds for their inhabitants. An alien standing on a neutron star's surface, where gravity is 1 billion times Earth's, would watch stars streak across the sky like comets as time outside races forward. Their biology would need to compensate, perhaps with nerves that fire in picoseconds or muscles that contract over days. Communication with such beings would be a nightmare. Their quick reply might take our years to receive, their concept of immediate, utterly alien to our impatient human rhythms. Even within our own solar system, time perception shifts subtly. Astronauts on Mars, where gravity is 38% of Earth's, might process stimuli a fraction faster than we do, their bodies and brains adapting to a slightly sped-up time frame. Over generations, colonists there could evolve internal clocks distinct from Earth's, their daily rhythms skewed by the planet's 24.6-hour day. Scale this up to interstellar civilizations, and you've got a universe where now is a fluid concept, shaped by the gravity well you're born in and the metabolic tempo of your species. So the next time you miss a fly with a swat or marvel at a hummingbird's blurring wings, remember, you're witnessing alternate realities of time perception right here on Earth. And out there in the cosmos, the diversity could be far stranger, with entire civilizations experiencing lifetimes in what we'd call a breath, or stretching a single thought across our centuries. Time isn't just a universal constant, it's a personal experience, as unique as the biology and worlds that shape. What if everything you learned about early medieval history was an elaborate fabrication, a massive conspiracy stretching centuries? That's the jaw-dropping claim of the phantom time hypothesis, a fringe theory proposing that nearly 300 years of history, from 614 to 911 AD, never actually happened. According to this audacious idea, Holy Roman Emperor Otto III and Pope Sylvester II colluded to invent a fictional past, doctoring documents and forging events to place themselves at the center of a grand historical narrative. If true, our current year wouldn't be 2024, it'd be the 1700s, and Charlemagne's entire empire might be little more than an elaborate fairy tale. The theory hinges on curious gaps in the archaeological record and chronological inconsistencies in ancient texts. For example, periods like the so-called Dark Ages left fewer surviving artifacts than other eras, leading some to speculate they were simply inserted later to pad the timeline. Even celestial events like eclipses, often used to verify historical dates, could allegedly be misdated or misinterpreted. Proponents point to architectural styles that seem to evolve abruptly, as if centuries of development were compressed into decades. It's a seductive thought experiment. What if history's scaffolding was bolted together by medieval power brokers with an agenda? But before you recalibrate your calendar, let's unravel why mainstream historians dismiss this as pseudo-history. First, the conspiracy would require thousands of scribes, scholars, and rulers across Europe, the Middle East, and China to participate in silence, a logistical impossibility in an era without centralized record-keeping. Dendrochronology, the study of tree rings, provides unbroken climate records that align perfectly with the traditional timeline. Ice cores from Greenland and Antarctic glaciers show volcanic ash layers dated to the missing centuries, while Chinese and Arab astronomers documented celestial events like supernova that match our established chronology. Even the Mayans, worlds apart from European politics, kept calendars that independently corroborate the timeline phantom time theorists claim was invented. The real fascination isn't the hypothesis's validity, it's what it reveals about our relationship with time and history. Humans crave narrative coherence, and gaps in the record unsettle us. The phantom time idea thrives because history is messy. Records get lost, artifacts decay, and contradictions emerge. But rather than embracing uncertainty, some minds spin tales of grand deception. It's the same impulse behind modern conspiracy theories, a desire to replace randomness with intentionality, even if that intention is nefarious. So while we're not secretly living in the 18th century, the phantom time hypothesis offers a playful reminder. History isn't just a sequence of facts, it's a story we collectively choose to believe. And sometimes the wildest tales teach us the most about why we trust the clocks, calendars, and chronicles that shape our sense of time in the first place. Dark matter and dark energy, the two most enigmatic forces shaping our universe, might be silently warping time itself in ways we can't yet measure. Picture dark matter's gravitational grip, invisible yet so powerful it bends light and sculpts galaxies into being. Now imagine what that unseen mass does to time. Just as Earth's gravity tugs ever so slightly on your wristwatch, dark matter's colossal gravitational fields, far stronger than anything in our visible cosmos, could be twisting time into unrecognizable shapes across vast galactic distances. Clusters like the Bullet Cluster, where dark matter's gravity visibly separates from ordinary matter, might also be pockets where clocks tick at bizarrely different rates, hidden by the very fact that dark matter doesn't emit or reflect light. We're left with a cosmic riddle. If time bends around visible mass, how wildly is it contorted where dark matter dominates? Then there's dark energy, the phantom force accelerating the universe's expansion. Unlike gravity, which slows time near massive objects, dark energy's repulsive push might be stretching space-time itself, not just expanding space but diluting time's flow across cosmic scales. Think of it like inflating a balloon while the rubber grows thinner and thinner. As dark energy accelerates galaxies apart, the intervals between cosmic events, supernova, star formations, could appear elongated from our perspective, a kind of temporal redshift to match the light stretching. Some theories even suggest dark energy's influence could grow so dominant that in the distant future, time might effectively freeze in regions where expansion outpaces all other processes, leaving pockets of the cosmos eternally locked in a single moment. The wildest possibility, dark matter and dark energy could be two sides of the same coin, their interplay sculpting time's hidden architecture. In certain unified field theories, dark matter's gravity might create localized time warps, while dark energy's expansion smooths time's flow on larger scales. Picture a cosmic hourglass, dark matter clusters acting like knots that slow time's sand, while dark energy widens the neck, speeding its passage elsewhere. Observations of distant supernova already hint at this. Their light curves appear stretched not just by space's expansion, but by subtle time dilation effects that don't fully align with known physics. Could dark energy be subtly rewiring time's rules in the voids between galaxies? Until we unravel these mysteries, time's behavior in the dark cosmos remains one of physics' great open questions. Every galaxy rotation curve that defies Newton's laws, every millimeter-precise measurement of the universe's accelerating expansion, quietly whispers that our understanding of time is incomplete. Perhaps future probes, like gravitational wave detectors tuned to low frequencies, will catch echoes of dark matter's time-bending ripple, or maybe dark energy's fingerprints will surface in tiny deviations in atomic clocks placed in deep space. One thing's certain, in the dark sectors of the universe, time isn't just ticking, it's bending, stretching, and hiding secrets we've only begun to chase. Given enough time, trillions upon trillions of years, something impossible becomes inevitable. That's the unsettling premise of the Boltzmann brain paradox, a thought experiment that twists our understanding of time, consciousness, and reality itself. Imagine the cosmos in the far, far future, long after stars have burned out and black holes evaporated. In this cold, dark void, quantum fluctuations, tiny, random bursts of energy still flicker in the emptiness. Most of these fluctuations vanish instantly, but given enough time, even the most improbable event will eventually occur, including, bizarrely, the spontaneous formation of a fully self-aware brain, complete with fabricated memories and senses, popping into existence for just a moment before dissolving back into the void. This isn't just sci-fi speculation, it's a legitimate consequence of statistical mechanics. Austrian physicist Ludwig Boltzmann first proposed that in an infinite or near-infinite timescale, even highly ordered states like a functioning brain can emerge from chaos purely by chance. The likelihood is astronomically low, but infinity plays by different rules. Given eternity, every possible configuration of particles will recur infinitely, including one where your thoughts, your memories, even this very moment you're experiencing, are nothing more than a fleeting accident of entropy. The paradox forces us to grapple with deep questions about time's nature. If the universe lasts forever, are we more likely to be real beings in an ordered epoch or temporary hallucinations in a sea of randomness? Some cosmologists argue that Boltzmann brains undermine our trust in reality itself. After all, if disembodied brains outnumber real observers over infinite time, statistically speaking, you're probably one of the illusions. This unsettling logic has led scientists to propose that the universe must have a finite lifespan, because if time truly were infinite, we'd almost certainly be Boltzmann brains ourselves, a conclusion so absurd it suggests our models are missing something fundamental. But here's where it gets even stranger. The paradox isn't just about far future quantum flukes, it challenges how we perceive time's arrow. Normally, we assume memories prove a continuous past, but a Boltzmann brain would remember a history that never happened. This blurs the line between real and imagined time, suggesting even our sense of duration could be a fleeting artifact of particle arrangements. The universe might not need a true beginning or end, just enough time for random fluctuations to simulate them. While no one seriously believes we're Boltzmann brains, the thought experiment serves as a cosmic cautionary tale. It reminds us that infinity plus time equals madness, that our grip on reality relies on the universe having boundaries, whether in space, time, or the laws of physics themselves. Perhaps time isn't an endless canvas but a finite story, one where improbable events stay improbable, and our existence isn't just a glitch in the void. Or maybe, in some unfathomably distant future, another version of you is reading these very words, momentarily conscious in the dark, wondering the same thing, before vanishing into the silence of eternity. Time might be the most persistent illusion we've ever experienced, a trick of perception so convincing that entire civilizations have built clocks, calendars, and cultures around it. Yet cutting-edge physics whispers a startling possibility. Time isn't woven into the fabric of reality at all. Think of it like the glow of a neon sign. It feels vivid and real, but it's just a side effect of invisible electrical currents buzzing behind the glass. Some of the boldest theories in physics, from holographic principles to quantum gravity, suggest time could be just like that glow, an emergent phenomenon hiding a deeper, timeless reality. Take the holographic universe theory, which paints our 3D world as a cosmic projection of information encoded on a 2D surface at the edge of space. In this view, time isn't a fundamental dimension but a kind of collective hallucination, like the moving images on a movie screen made of static frames. Just as a flipbook creates the illusion of motion, the universe might create time through quantum interactions we don't yet understand. Experiments with black holes lend eerie support to this. Their entropy, a measure of disorder, scales with surface area, not volume, as if the 3D world is just a rendering of data stored on a 2D boundary. If true, time could be a narrative stitched together by our brains to make sense of this underlying code. Even loop quantum gravity, which imagines space-time as a web of tiny, indivisible atoms, treats time as a secondary feature. At the Planck scale, these quantum loops interact in ways that don't require a background clock. Time emerges from their relationships, like the rhythm of a symphony arising from individual notes. Picture a crowd doing the wave in a stadium. The motion feels continuous, but it's really just people standing up and sitting down at the right moment. Similarly, time's flow might be a collective effect of quantum events aligning in ways our macroscopic senses interpret as duration. The most radical ideas come from quantum mechanics, where particles can exist in superpositions, multiple states at once, until observed. If reality at its smallest scales doesn't choose a state until measured, does time truly pass, or is it a series of discrete nows that only seem connected? Some interpretations suggest the universe is a vast network of correlations, with cause and effect being statistical tendencies rather than ironclad rules. In this view, the arrow of time might just be our brains stitching together probabilities into a coherent story. Here's where it gets existential. If time isn't fundamental, what does that mean for free will, memory, or even the idea of cause and effect? Philosophers like Julian Barber argue that the universe could be a timeless landscape of nows, with our sense of progression being a psychological artifact. Imagine a gallery where every possible moment hangs like a painting. Your life isn't a film reel but a collection of frames, and your brain's perception of moving through them creates the illusion of time. Yet for all its strangeness, this perspective solves real puzzles. The Big Bang singularity, where general relativity breaks down, might not need a before if time isn't foundational. Quantum entanglement's spooky action could make sense if particles are linked outside temporal constraints. Even consciousness, which stubbornly feels like a continuous stream, might be the universe's way of translating timeless quantum data into a narrative we can experience. So the next time you check your watch, consider this. Those ticking seconds might be no more fundamental than the warmth of sunlight, a surface effect of something far deeper and more mysterious. The universe doesn't need time to exist. It might just need creatures like us to believe it does. And in that thought lies the ultimate cosmic joke. Time, the very thing we've built our lives around, could be the most convincing illusion of all. From black holes freezing time to quantum particles existing in multiple moments at once, our journey through time's mysteries has shattered every assumption we once held. Einstein showed us time bends like rubber near massive objects, while the quantum realm proved it can blur, loop, or even cease to exist at the smallest scales. On cosmic stages, entire galaxies experience time in slow motion due to the universe's expansion, and theoretical time machines lurk in the math of relativity. Even our own planet isn't immune. GPS satellites prove time ticks faster just a few hundred miles above your head. The wildest takeaway: time isn't a backdrop to the universe, it's a player shaped by gravity, motion, and observation. A second here isn't a second there, and now is a personal illusion fracturing across the cosmos. Whether it's Boltzmann brains hallucinating reality in the far future, or the spine-tingling possibility that time itself is an emergent hologram, one thing's clear: the universe operates on rules far stranger than fiction. So which fact shattered your perception of reality? Was it the antimatter time reversals, the cosmic stretches making billions of years vanish, or the eerie chance that time might not exist at all? Drop your mind-blown moments in the comments. We're obsessed with these cosmic riddles too. And if you're hungry for more universe-bending mysteries, hit subscribe. From wormholes to white holes, dark matter to quantum leaps, we're just getting started. The cosmos has endless secrets left to unravel, and we're diving deep into every one. Your clock is ticking, but as you now know, even that isn't as simple as it seems.